Divergence theorem. Another one we will discuss Gauss divergence theorem. Before going to discuss the Gauss divergence theorem, so we know that the divergence means that is delta dot d delta dot a is equal to divergence is equal to divergence. For example, divergence of vector a is equal to del dot a. We learn divergence, curl, and the gradient also. Same way for the Gauss divergence. Before going to discuss the Gauss divergence theorem, so 1 minute will take for this. What is the divergence of d or something? What you know basically that. For example, I consider a point P. Okay, point P, it is in the region of charges. Point P, it is in the region of charges. This is the charges. Okay, point P, it is in the region of charges. Okay, so P is the region of charges. Delta V, it is the charge density in the over the point P or at the point P. Due to the charge, there will be the electric field around the P. Then it can be shown. Okay, it can be shown x-axis, y-axis, z-axis. It may be. What is that? Dou dx by dou x plus dou dy by dou y plus dou dz by dou z. Okay, is equal to rho v, because x-axis rate of change of flux density, rate of density along with x, y, z is equal to is total charge density rho v z. Or we can take the common dou by dou x plus dou by dou y plus dou by dou z and all, taking dou separate is equal to rho v. We know that from the divergence. So this all will what will write, this is the del only, this is the del, sorry, this is d will take dx dy dz. Okay, dx dy dx plus dy plus dz, that also equal to d only. Therefore this dot is equal to d is equal to rho v. Okay, this can be written simply in the Gauss divergence theorem. Okay, for the introduction purpose, where I am going to use this equation in the coming Gauss divergence theorem, I will write. What is this? What I wrote here? I consider a P in the charge. Okay, in the region of charges, due to there are charges. Let P rho v be the density charges at P. Due to the charge, there will be the electric field around this P. Okay, it can be shown, maybe it is in the x direction, y direction, d direction along with the d vector. That can be like this. If we simplify this, means we'll get this. You remember this equation number 1 or something for this. Now we'll start the Gauss divergence theorem. What is the statement for the divergence theorem? For example, the same closed path I am taking here. Closed path. This will big is the volume B. This Gauss means this is a Gaussian surface. The charge is enclosed within the imaginary surface. This is a Gaussian surface. We know that. Consider a small element. Consider a small element. Okay. This is a small element that is called delta V. These are there. Okay. By using this, we can give the statement for the Gauss divergence theorem, like how the integral of the normal component of the flux density over the any closed surface in an electric field is equal to the volume integral of the divergence of the flux throughout the space enclosed the surface. Okay, the same statement can be represented by in this way: the closed surface but D ಯಾರ್ದು ಈ ಸರ್ಫೇಸ್ ಆಮೇಲೆ ಓಕೆ ಗೋ ಕಟ್ ಇಟ್. Closed surface. Okay, what is the statement? The integral form of the normal component of the flux density, this is the flux density over the closed surface ds is equal to it integration of its volume is v. Okay, into d. Okay, dv. This is the statement. This you can prove this. Okay, or proof, take it a proof. Okay, these are the conditions. So same thing once again I will take the data I given. What is the v is the whole volume, delta v is the small volume, d is the density of these charges, that all. So that I will write here. Okay, let delta v is the volume, element volume. For example, q is the charge, means what we call delta q is the small element charge. Like once again, this is the dv is the element charge and delta q is the element charge. Whole charge, sum of these charges also called as a capital Q. These are the some fundamental. If rho is the charge density and since rho is a very continuous to in the volume throughout the surface. By using this, we can write as delta v rho v, the charge density throughout the volume can be written as a limit of delta v small area tends to 0, or the change of element charges by volume charges. Okay, or this can be written as dv tends to 0, limit of this means you can write dq by dv only, dq by dv only, dv nothing but delta v only. So this is it. Or we can cross multiply this, means this is a rho, cross multiply dq is equal to rho v, v means along with the charges along with volume, charge density along with volume is into what we call dv. This is, so if q is the total charges over the surface, therefore dq can be written as q is equal to integration of this, dq is equal to integration of v, okay, rho v into dv. This is Gaussian surface. Okay, now wait, but we know that, okay, in the last introduction part, what divergence of del d is equal to rho v. We know that del of d vector is equal to rho, or it is one of the Maxwell first equation. It is one of the Maxwell first equation. Therefore this q can also be written as integration of v, okay, del v can also be written del of d rho v, okay, this is a rho, no, del of d, okay, into dv as it is, this dv as it is, we can write. Now by applying the Gauss law of the Gaussian surface, what is the Gauss law? Gauss law is equal to closed surface, okay, of its density of over the surface is equal to total charges, okay, total charges is there. By using this equation and this equation, you call this a equation, b, by a and b equation we can write this as, this is also q, this is also q. So equate these two equations, then I will write here, then okay, what will write the closed surface d of ds, okay, d of ds is equal to, okay, over the integration volume of d of d, okay, into dv. Wait, so this is the statement of the divergence, Gauss divergence theorem, okay, d dv ds is equal to dt, okay. So this is the Gauss divergence theorem, or simply the divergence theorem, what we know that. Is it clear? Close it.